So I personally found this question, compared to other step questions, pretty straightforward. One of the hurdles might be spotting the first step, but luckily, if you practice enough integration, it's kind of intuitive what to do. Okay, so we're given this strange integral. Now notice, what kind of integral is this similar to? Here's one it might be similar to. Let's call this IS, standing for I similar, I guess. So if you've seen this trick before, the whole question becomes pretty nice. Okay, this integral here is doable. Very doable. So why is that? Well, it's simply the special case where you have the presence of the derivative beside the actual function itself, which means that if I differentiated this function to the power of n, I would end up getting n times the function, right? So let's do that normally. Sorry, let's pretend that's n plus 1. That's what I meant to say. You would get n plus 1 times the function to the power of n, and then you'd have to use the chain rule and add in their derivative. Okay, does that make sense? So I explained that quite poorly. Let me give you an example. Suppose we had 2x multiplied by x squared plus 4 to the power of 9. Well, I know that integral is going to look very like, hang on, I scroll down too far there. That integral is going to be very like x squared plus 4 to the power of 10, okay? Because simply if we differentiate this guy, I'm going to have 10 x squared plus 4 to the power of 9 multiplied by 2x because of the chain rule. So we see that the presence of the derivative beside the actual function is very useful. And this is a trick that no one's really given a name to that makes sense. And I had a teacher back at my school called Dr. Brown, and he decided to call it the elephant. So I'm going to go with that. So this is called the elephant integration trick, I guess. So anyway, this here would be the presence of an elephant, right? But the only adjustment we have made is that instead of having f of x, it's now f of x squared. Okay. So that's kind of interesting. And it kind of gives us a clue as to how to do the question. But, well, let's read the rest of it, shall we? So when n is a positive integer, we got to show that if the function satisfies a very strange looking property here, for some constant k, then, you know, it can be integrated rather easily. Okay, and you get an expression in terms of all of that stuff there. So why would this have anything to do, you know, like what are we tempted to do right now? Maybe we want to use this property straight away. Like, I don't really know. Well, bearing in mind that if we had the integral, the one below I similar, what can we do with this now? You know, that is the real question. So what springs to mind then is by parts, right? But how exactly? Right, well, what is the trick? Well, let's try by parts with just I guess normally and see what happens. So I mean, well, it's step. Let's just jump in and start playing about with things and see what happens, right? So if we tried by parts, I guess intuitively one might say that, well, we can't really integrate this thing, so we're gonna have to say that's our u. And oh dear, well, we can't integrate that thing either. Interesting. So what do we do? Well, if you notice my trick from earlier, we can use different parts. We can say, okay, well, maybe if I split the squared up, then I can have this here. Because now this is integratable. That's the part of n, and then a bracket outside that. Okay, so we couldn't do by parts on it as it was because we can't really integrate the differential squared, so we can't have that as v dash. That would be bad. But here we can have that as v dash, and I guess this is u. Okay, so we're gonna have you know, if we do by parts and that. Again, we're going to have uv. I can work this out later. What I care about is the integral v u dash. Is that feasible? Right, so if this is v dash, then v, well, we can work it out. It's just going to be 1 over n plus 1. And I'm just going to write f to the n plus 1 there, which is, you know, that is f of x to n plus 1. But, I mean, we're all clear on what that is. And then u dash. Well, u dash is just f double dash. Okay, dx. Now, okay, well, that's not really good, is it? But looking back at that property, perhaps now is the time to use it, right? So, I mean, it's given us if f double dash is that thing. So we think, okay, well, I guess let's plug that in and see what happens, right? So, what will happen? Well, I'll take the 1 over n plus 1 outside. Make things simpler. So I have f to the n plus 1. And I'm substituting this in for k times f dash times f. Okay. And yay, that's actually going to give us something that we can integrate. You guys see that? So that's going to be integral of f to the n plus 2 times f dash. And again, this is the elephant once more. Sorry if you don't like that name, but, you know, I'm sticking with it. It sounds kind of ridiculous, but I love it. So this is durable, right? So, I mean, what is that? That's just going to be 1 over k n plus 1. This is going to be, well, again, using the same trick, that's going to be simply f to the n plus 3 divided by n plus 3. Plus whatever constant of integration we have. That would be an annoying mark to lose in step. So if we go over here, then we see that, oh yeah, we're nearly done. We just have to calculate uv. So u is our f dash, and v is that 1 over n plus 1, f to n plus 1. Okay. So that's okay, I guess. So I'll just write f dash, f to the n plus 1 over n plus 1. So we see that is our property right there. Hopefully, if I did that right. But yeah, that is what this expression evaluates to become. Very interesting. Now, the next few bits are quite a lot of meaningless algebra slugging, right? Which is something you need to get good at in STEP. And I don't think me going through the lots of algebra on video will be very beneficial. But if anyone wants me to do that, I will. But I want to have as much time as possible to get ideas across to you guys that are going to benefit you the most. So rather than slogging through lots of gunk, I'll just talk about how I would approach the question and then how I would slog through the gunk rather than actually doing it. Okay, so we see that we want to verify it in the case that f of x is tan x. The first time I saw this, I was a little confused. Then I realized, well, all they're really asking you to do is, will this work if f of x is tan x? Well, if f of x is tan x, what is I? So I works out to be, well, the differential of tan is sec squared. So that's going to be sec to the 4 times tan to the n x dx. That's what I would be. But remember that you can only evaluate I in that certain way if this property here is satisfied. Okay, so you need to check that works for tan. So let's do that over here. So again, that property is we want the second derivative. We want the second derivative of tan to be some product of its first derivative on itself. Okay, so if f is tan x, then f dash, or f dash of x is sec squared x. Then f double dash is 2 sec squared x tan x. Okay. That just comes from, well, you get your sec there, and then you're taking the 2 times sec x, and then we fix it with the chain rule. The differential of sec is sec tan. All right, so now, does that satisfy our property? Well, notice that f dash is indeed, well, that's 2 multiplied by f dash multiplied by f. Interesting. So it does satisfy that property, right? You know, going back to that property over there, we see that, well, k is 2, right? So that's interesting that they made us do that, because now they're asking us to evaluate something which looks like we could squeeze a tan in there, right? Like, I mean, this must relate somehow to this part of the question. In fact, it does, right? I mean, if we think about this for a second, well, this integral, well, if we try and fit a tan to it, right? You guys get that? It's like, okay, well, if the tan is here, and they've asked us to do some stuff with tan, maybe we can relate this to tan. So that would be like, well, that's going to be 1 over cos to the 4, and then it's going to be tan to the 4, right? Sin over 4 cos to the 4, and this here is just going to be sec to the 4. So you see that that's applicable to verifying it. Okay, we just set n equal to 4. All right, and once we do that, we can go through that whole process using what we have found using our weird formula here. We don't even have to evaluate the integral. All we've got to do is plug it into this guy here, in orange there. You know, so we plug in the necessary values, and we're done. Okay, so in other words, that integral will become, well, this is, you know, that's like tan, so that's like sec squared. You know, you just fill everything in basically with n equal to 4 and k equal to 2. Okay, so yeah, etc. etc. Oh yeah, so it asks us to verify it for f of x is tan x. So in order to verify it, what we need to do is well, it's very simple. You just simply check that the property is satisfied, which it was. Okay, so this blue property here, now I'm drawing a red box around it. So we checked that was satisfied for f of x equal tan x, and that was fine. It was. And then what we wanted to do was verify that this is actually true, like what our result holds for when it's tan x. So what we can do there is we just take this, plug tan in as f of x, right? So our I will become integral of sec to the 4, you know, tan x, tan to the n dx, x dx, and do what we just did, and you know, show that relates to the same formula. Alternatively, might be a bit easier. If we take this formula and we plug in f is tan of x, right? So let's simply put f is tan of x in there. So tan x, and then this would be, you know, sec squared x and whatnot. Well, if we differentiate this whole thing, we should get sec squared. Okay. I'm sorry, no, that's nonsense. If we differentiate this whole thing, we should get the integral we started with. Okay, does that make sense? So if we differentiate our result, our evaluation of the integral, if we differentiate, we should get right back to this thing here. Okay, so that's another way to verify it. Anyway, so part I turned out to be fine if you spotted that tan was there. The tricky part now, okay, so that's probably about, like, I don't know, I guess 12 marks out of 20 of the question. That would be my guess. This thing here, okay, well, what is this? Somehow it must relate to what we did. Okay. Well, this is kind of interesting. Maybe a bit daunting at first, but remember, we're looking for some function that satisfies this property. I'm drawing another red box around it. Okay, so what would satisfy that property? Well, let's pick this dude here. can we set f of x equal to that? Well, we can only do that if the second derivative of it is equal to some constant times the first derivative times itself. Okay, so suppose we say f is equal to sec x plus tan x. What I'm gonna do, if I was doing step, I would say let sec x equal s and tan x equal t, because you can tell it's gonna get a bit messy when we try and calculate all these derivatives. So f is s plus t. Now f dash is going to be what? Well, we're going to get differential of sec, which is sec tan. Then we're going to get the differential of tan, which is sec squared. And I can factor an s out of that expression, and I'm actually left with that. Okay, write it in alphabetical order, why not? All right, now differentiate again. Okay, so product rule, I guess, and we end up getting differential of sec is sec tan times s plus t. Differential of the thing inside then, well, we did that already, right? So that's st plus s squared. Okay, so what is this thing? Is there a clever way to factorize it? Well, yes, there is. Let's take an s outside. We have t of s plus t. Notice we can take another s outside of this guy. So that becomes s of s plus t. Okay. So, in other words, this s went outside first, and then we can factor these two s's out to get another s plus t there. And notice that's t s plus t plus s plus t. So that is actually going to be s times, well, what's t s plus t plus s plus t? You'll notice that is actually s plus t squared. Okay, now remember again that blue property, the blue-red property, whatever, was this dude here. It was is f double dash equal to some constant times f dash times f. Is it? Well, I mean, let's check. So we have f double dash here. Okay, that's our f double dash. Let's calculate f dash. So if we do that, we end up getting these guys combined, and we get s of s plus t squared. So for a constant k equals 1, this is satisfying that property. Hooray, right? That means that we can validly do that. That's fine, okay? So that will actually work if we set f to be that. Remember f dash, what was f dash? Well, f dash was equal to s plus t. Okay, so if we can get f dash squared, that is simply going to be s squared times s plus t squared. Now going up to that, okay, so we have sec squared, sec x plus tan x to the 6. So what we can do now is rewrite that integral as sec squared x. And remember, we want a sec x plus tan x squared. Okay, and then we're going to multiply that by what's left. Sec x plus tan x. And what's left would be, well, you know, what's 6 minus 2? That would be 4, hopefully. I'm correct in saying that, hopefully. These videos do fall on my head sometimes, so I may make some ridiculous mistakes. I'm sorry, but this here, okay, well, I mean, yeah, that's just f dash of x squared. And this guy here is just going to be fx all to the power of n. Hooray! All right, so we're basically done. All right, so you know, now we see, well, this is the same result for k is 1 and n is 4. So all we got to do is take our expression and plug it in, and we're done. So that was really cool, spotting that trick, you know. And if you do that by yourself, you're gonna have quite a little nice feeling when you do that. But one thing that definitely makes it easier is trying, instead of writing all these trigonometric expressions out, you can, you know, just use s and t. Because once I did that, I saw it immediately. When I was playing about with secs and tans, the page was just messy. I was just like confused and crying and stuff. But like, no, I wasn't crying. I was close though. Steph has made me cry before. Step 3, not step 2. Well, actually, some step 2 questions. They can be pretty nasty, you know. I mean, I mean, I wouldn't say step 3 is any harder than step 2 necessarily. It's just different content. So it really depends on you. But one of my favorites is integration, just because I did a lot of it. And, you know, if you do a lot of something, you get better at it. So that's this question. I thought it was, you know, pretty okay. There's no horrendous tricks or anything that you specifically needed to know. So I hope you guys enjoyed watching and have gained something from this video. And if you watch this without trying the question yourself, you're a bad person. No, I'm kidding. No, well, I'm only half kidding. You should really be trying every question yourself and not looking at any solutions and stuff until you're stuck for, I'd say, like 3 days or something. If you can't get it after 3 days and you've tried at least 3 times a day for 3 days, then it's okay. Or maybe if you're starting out, it's okay to look at a few solutions to get a feel for how they do it. But you know what Sigla says in the start of his book. Anyway, I'm rambling on, so I'm gonna cut out of here, guys. So thanks for watching.